Good afternoon and welcome back, everyone. We'll give folks a couple of minutes to trickle in here. And as always, I have another poll in the chat box off to the right. I get a sense of some baseline knowledge relative to energy management systems. Give it another 30 seconds or so. Just like last week, we have a good bit of content to get through today. I see folks still coming in. For those that are just entering, we have a poll off to the right, just trying to gauge current experience working with energy management systems. Great. All right, thanks. We'll get going. Looks like from our poll, about half of you have either some or substantial experience working with EMSs, and the other half have no experience. So this should be informative, hopefully for all groups. Okay, just our typical logistics. Today's webinar is being recorded. We're going to keep the audience muted for the duration. We ask that you put any questions in the chat box, and I will read them to Jeremy, our main presenter for today. We've got a couple of pre-scheduled stopping points where we'll go through questions. A couple of other logistical items. We are planning to send certificates of completion at the end of the session, end of session 5. These can be used for self-reporting of PDHs for those who have those requirements. And the QC of past recordings is still underway with NH Saves right now. I hope to have those posted shortly, and we will notify everyone once those do ultimately get posted. Okay. Quick refresher on us. GDS Associates, we're a multidisciplinary energy engineering and consulting group with a Northeast presence based out of Manchester, New Hampshire. My name is Matt Siska. I'm the manager of the Commercial Industrial Services Group. Our lead presenter today is our senior engineer, Jeremy Blanchard. Jeremy presented last week on M&V topics. Jeremy has nearly 15 years of experience working on a host of energy engineering related topics in the commercial, industrial, municipal sectors. Expertise in mechanical systems, M&V, commissioning and retro commissioning, and leads most of our technical projects. And as you'll find, he is also very knowledgeable about energy management systems, which is a really critical area. So today is the fourth of 5 webinars in our series. Understanding how energy management systems function and how they can be optimized is perhaps one of the most important topics that we will be covering in this series. In our day-to-day work, supporting commercial customers, we regularly encounter underutilized energy management systems. This can be due to limitations with existing systems, similar to how we've crafted the case study, where the primary EMS does not communicate with the VAV boxes, or just general lack of knowledge. One of my favorite anecdotes involves a scoping audit we did at a hospital a few years back. I asked if they had an energy management system. They said yes, and pointed me towards a 1980s looking desktop computer. I asked if they could fire it up so we could review some of the data, the set points and the trends. And the response was, oh, well, we don't know how to turn it on. Ernie was the only one who knew how to run the system, and he retired several years ago. So that was that. In all seriousness, there's a wealth of energy efficiency opportunity in most energy management systems. And that's what we're going to focus on today. Jeremy will start by walking us through the basic architecture of traditional energy management systems, then get into specific energy saving sequences and the types of opportunities that we look for while on site. Should be a fun session. Next week, we will be concluding our series with a discussion of smart building trends, including electrification, battery storage, solar, and electric vehicle infrastructure. I really hope that you will join us. With that, I will hand the reins to Jeremy to introduce learning objectives for today's session.
Thank you, Matt. So today's learning objectives are fourfold. First, we're going to review the different types of EMS components and communication protocols, graphics, and sequences of operation that exist out there. There's quite a few. We're going to emphasize the importance of EMS and how they are often inefficient and are opportunities for NH-SAVE's custom projects. We're going to highlight the best practice operating sequences and highlight the efficiency opportunities that exist. And lastly, we're going to explain the differences between retro commissioning and monitoring-based commissioning and when to apply those strategies. So let's first start with an overview of savings opportunities for EMS. We view EMS as the new lighting in terms of cost-effective and prevalent energy savings opportunities. These systems are often underutilized, lacking support and expertise, and can be outdated. Following the mantra we introduced in the M&V session, you cannot manage what you cannot measure, or in the case of an EMS, trend, using trend data. An updated modern EMS provides a wealth of information that can be used to manage and diagnose your HVAC systems. The potential for opportunities can span a wide range, including new construction, or you're putting in a brand new system, where commissioning is especially important, as we discussed in session 2, since it was amended out of the New Hampshire Energy Code. Commissioning EMS is really important to ensure that they're operating per design intent. Say you don't have an existing EMS, putting in a new system can offer many energy savings opportunities. For existing systems, the opportunities can range from a complete replacement to an integration and software upgrades, and everything in between. For systems with pneumatic controls, for example, you could replace the components to convert it to a full DDC system, or you might expand the system to incorporate additional capabilities, all of which can yield energy savings opportunities. If you have a new, or if you have an existing system or considering a new system, please be sure to reach out to NH-SAVES for technical assistance. So let's first start with the EMS architecture. The architecture of an energy management system can be quite complicated, as shown here, with several different communication protocols, networked access points, various supervisory and equipment controllers, and wireless equipment. So let's break it down into the 4 major components. Here we have the 4 major components: management, integration, field or equipment controllers, and the sensor or actuators, which I like to refer to as end devices. I'm going to take a bottoms-up approach to reviewing each of these components so we can build upon each layer, much like you might construct a pyramid. The lowest level are the sensors and actuators, or end devices. They operate and provide feedback for each piece of equipment. For example, you might have a space served by a VAV box that uses a room temperature sensor to let the EMS know when the space requires conditioning. Next is the field controller level. This is where the equipment is controlled based on feedback and operation of the end devices. Using that same example, the VAV box is now controlled using a VAV controller, which gathers information from the room sensor to actuate the VAV damper or other operations depending on the configuration. This level is where the most heavy lifting operation typically occurs. It's also where the equipment can operate without the higher levels above as a standalone system. This is also why I like to take a bottoms-up approach. So for example, that VAV controller can operate without connection to these higher levels. The integration or supervisory level is where the equipment controllers get integrated into one common EMS. This level is what allows the user and the EMS to have visibility and control into all of the equipment as one cohesive system. The supervisory controller, or the main brain, can pass information to and from each of the equipment controllers to achieve optimal operation. Say, for example, the motor shown here serves the chiller primary loop pump, or the water flowing through the chiller. The supervisory controller can vary the speed of the motor based on the demand of the chiller, based on feedback from the chiller controller, also shown here on the right. Communication protocol, or the language that an EMS uses to communicate, is very important at this level. Several different proprietary communication protocols exist and require specific equipment for compatibility. However, we recommend using an open protocol such as BACnet whenever possible to allow controllers from different vendors to be interchanged seamlessly. As a facility operator, this is likely important to ensure you're not locked into one controls contractor. And lastly, the management level. You may have one or more supervisory controllers within a single building, or your site might have multiple buildings where each supervisory controller exists for each building. The management level is where the supervisory controllers are pulled together into one common platform. The management level may also include a server that provides additional computing power for aspects such as long-term trend data, which we'll touch on a little bit later. Or web-based access, where the EMS front end can be accessed remotely through a web server or a web browser, or even your phone. Now that we've touched on the architecture, let's review the components of a basic EMS. You have inputs, outputs, and software points, the menu structure that we'll review, graphics, schedules, and trending, as well as alarms. So let's step through each of those components now. So the first component are the points. This is arguably one of the most important points as it builds upon, one of the most important components as it builds upon the additional components we'll talk about. So here we have inputs, which are signals from the sensor, such as a current transformer or a temperature sensor, to the controller that provides information regarding changing conditions. This differs from an output, which is a signal from the controller to a component, such as a relay, that performs an action on the end device, such as a damper or a valve. These are extremely important to distinguish because inputs are what is actually happening versus outputs are what you want to happen. For example, say a motor is commanded on, which is the output, through a VFD. However, the VFD is disconnected locally. Someone turned it off. Well, the output command point will say the motor is on. If you're looking at the screen and you'll think, oh, motor's operating. However, if you have the status point as well, which is an input, that will tell you whether the motor is really on. Oftentimes, inputs can be left out to save cost and are very important, particularly status points, where you'll have a current transformer over the wire that measures the amperage to know that the equipment is on. Lastly, we have software points, or often called virtual points. These are points that are calculated or passed through the controller, as opposed to being physically hardwired points such as inputs and outputs. These points are used to establish points that are maintained, such as set points, or to provide monitoring and diagnostic feedbacks, such as alarms. So here's an example of an actual schematic for a controller, where inputs are on the left and outputs are on the right. The example we're showing here includes fan status inputs, as well as a charging station. This particular building has a forklift charger that when it's charging, it requires a fan to operate to provide exhaust. While the fan is on the right-hand side as an output to turn the fan on, and the input is the charging station status. Let's talk about the next component of menu structure. This is an example of an EMS with multiple buildings. Each EMS is visually very different, but they all provide similar menu structure with access to the component tree shown in green to the left and the main menu shown in right. The component tree allows you to expand the drop-down under each building to navigate to various systems within each building. The main menu provides access to graphics, schedules, alarms, trends, and other settings for the building selected on the component tree. And here we have another example of a single building EMS front end, where there is no component tree structure because you only have one building, but rather a main menu shown in red for accessing the trending and alarms in a similar fashion. In this case, it's collapsed, so when you click that button, a pop-up shows up to show you the various options. Here they break out the floor plans and the equipment through direct buttons shown in green and are organized by equipment type. So on the left-hand side, we have a bunch of miscellaneous terminal systems, whereas in the middle at the bottom, we have all of our main rooftop units and the floor plans to the right. So digging into floor plans, here we have an example of an antiquated older floor plan that shows the space temperatures, terminal units such as VAV boxes and fan-powered terminal units. Clicking any of these boxes will navigate directly to that unit. So we're going to show a whole host of different graphics for different floor plans, HVAC, renewable systems, lighting, and metering to provide a flavor of the different options available. This is not intended to be an exhaustive list of graphics. We've also covered up a lot of the site-specific information and EMS vendors, so there may be a little details that are missing that you might expect. So to complement this more outdated floor plan graphic, we'll show a more modern floor plan, often referred to as a thermograph, because the color of the space corresponds to the deviation from set point. We've enlarged the legend down at the bottom that shows what each color represents. We can see here that most of the spaces are ideal, or they're meeting their set point. However, the auditorium, this big box in blue, happens to be a bit cold, showing by the blue color. We can also see that some spaces are not communicating, indicated by the purple. So there's probably a problem with the network or the controller for that space. Next, we'll dig into some HVAC units. Here we show an outdated rooftop unit graphic with crude boxy type graphics, minimal inputs and outputs and set points. There's no information, for example, on the return or mixed air temperatures, the outside air rates, the damper position, or the economizer operation. You have no idea how those things are operating, and it's very difficult to diagnose without that information. In comparison, here's a modern RTU graphic showing numerous control and feedback points. Now we can see the mixed air damper is 64%, which indicates the outside air damper is nearly 40%. That would be something we'd want to understand, as a more typical design is around 20%. Perhaps the unit is economizing. There can be a wealth of information available from such graphics that are useful during a retro commissioning study that we'll talk more about later. Here is an example of a more complex HVAC system referred to as a hot deck, cold deck unit. This is an extremely inefficient system that provides hot air in this example at 92 degrees and cold air at 55 degrees simultaneously in the bottom right-hand corner. Mixing boxes within the zones will blend the hot and cold air to achieve the desired space conditions. These units are extremely inefficient, but they're also very good at maintaining space comfort. Systems such as these are potential for VAV conversion, but can also be quite costly depending on site-specific conditions. Here's another example of an HVAC unit for an operating room air handler with even more points and a lot of congestion on the screen. Here we see 2 return and supply fans and 2 chill water coils, one a local chiller and one served by the central chill water plant to provide redundancy for this critical life-saving space. Next, we show a chill water plant. In this case, it happens to be a water-cooled chiller plant, showing a primary water distribution with 1 primary pump for each chiller, as well as a dedicated pump for the water side economizer, labeled HE1 at the top of the screen. The secondary side only includes 2 pumps and the main supply and return temperatures. Note that the chiller load is shown in the lower left corner, which is likely calculated based on the flow rate and temperature difference also shown on the screen. Wouldn't it be great if they also included a power meter, as we discussed in the last session, and showed the chiller performance, perhaps in kW per ton, that the operators could use to ensure the plant is operating efficiently? Next, we show the condenser side of the same chiller plant from the previous slide, showing the pumps, the sump basin, and the cooling towers. Note here they have 3 condenser pumps for 2 cooling towers to provide N+1 redundancy. We also see the free cooling pump at the top. Note that they are operating both fans for each cooling tower at around 80%, which is more efficient than operating 1 tower with both fans at 100%, assuming that that tower could meet the load. But generally speaking, operating more cooling towers at a lower speed if they have VFDs is more efficient than operating 1 at full speed. Next, we show a modern air-cooled chiller graphic where we can see chiller set points in the top left, capacity information on the middle left, and outside air limits and economizing set points in the lower left. There's a lot of information available for this one unit on this graphic. The chill water reset is shown in the upper right, with the pump information also shown on the lower right. And here is an example of an antiquated hot water system graphic with no system layout and very few useful control points. If your graphics look anything like this, please reach out to NH Saves for support, because there's guaranteed to be some energy savings. Here is a modern boiler plant for a wood-burning biomass plant. We can see the two boilers to the left with their primary pumps. Information for the secondary pumps, P1 and P2, is shown in the middle. The main supply and return distribution is shown to the left. Note this plant also measures the load based on measured flow rate and temperature differences. Coupling this load information with the delivered fuels, which in this case will be difficult to meter since it's a bunch of wood chips, would also provide efficiency feedback similar to the chiller plant mentioned earlier. In this case, you could do a monthly efficiency or a weekly, depending on the delivery of your wood chips. Next, we'll go through some terminal units. Here's an example of an old graphic for a terminal unit. In this case, it's a fan-powered VAV box that the site refers to as a fan terminal unit, or FTU. Primary supply air from the main air handler is provided on the left, with the airflow modulated by a damper. Typically, the primary air is only needed for ventilation and cooling. Heating for the space will be provided by hot water coils shown downstream of the secondary air at the top of the graphic, which is also the same as mixed air from the space, provided by the fan shown to the right. Despite being an old graphic, there's actually quite a bit of good information on this that you would typically expect for a terminal unit. So just because it's old and antiquated doesn't necessarily mean it's lacking. Next, we show a couple of modern examples of terminal units, including a VAV box on the left side, where here we show the space temperature trend over the last day, which is really useful for diagnostic feedback. Say you get a hot or cold call, you can look at that trend and see what the space temperature has done over the past day. The right graphic shows an infrared or IR heating unit that is controlled based on occupancy. The IR heater is currently in standby status, which means there is no movement in the space and the set point has been lowered by a couple of degrees. Once someone enters the space and motion is detected, the set point will increase back to the occupied value and likely the unit will fire. Here we show a summary screen for several induction units. Incorporating these summary screens when you have terminal systems or lots of spaces can be a really good way to review several units or spaces without having to navigate to each unit. And it's really important to include in your system. It's a really quick way to reduce the number of mouse clicks you have to make to look at a large number of systems. Next, we're going to provide some interesting examples that may or not be common depending on your perspective. The first example we have is a fully integrated lighting controls for both interior and exterior fixtures. The common area lighting for this mostly office building can be controlled directly from the EMS. You click the little drop down where it says lights on and you can turn the lights off. For the non-common spaces in this building, such as offices and conference rooms, they actually use the lighting sensors, the occupancy sensors, to control the VAV boxes, providing optimal occupancy-based controls for this building. Next, we have an example of a laboratory hood, showing the control valve on the hood exhaust is closed. To the left, we can see the associated makeup unit, providing around 800 CFM, and also heating with the valve at about 47%. Interestingly, the total exhaust flow shown in the upper right is over 800 CFM, which would indicate the hood flow is incorrect, or there's other exhaust not shown, or issues with the valves. Who knows? This is an example of where you always want to question the values you see on an EMS screen. Trust but verify is a great lesson to live by when reviewing EMS graphics. Next, we have a solar thermal hot water system that's connected to a domestic water heater in the building, shown at the bottom, as well as the geothermal loop through a heat exchanger shown to the right. Next, we have a graphic that shows a rainwater collection system that offsets domestic water for the process use in this facility. This graphic also serves as a dashboard with several meters integrated into this graphic to provide monthly totals as well as current demands for electricity, gas, and domestic hot water. And lastly, we show an example of electric power meter showing the demand trend over the past day, as well as a bunch of summary information. This builds upon the session we talked about last time, where integrating power meters and other various meters can provide useful information about your facility. The next component we want to talk about is schedules. Schedules outline when the equipment should turn off and on and are especially important for energy efficiency, since many systems can be turned off during unoccupied hours, but we often find equipment running 24/7, as shown in the example to the left, where each bar corresponds to a day, and the length of that bar corresponds to the hours that it operates. The example to the right, on the other hand, shows Monday through Friday, 5:30 to 8:30, plus 6 a.m. to 3:30 on Saturday. You always want to ask yourself, can these hours be reduced? Is operation on the weekend required? These are important questions to consider. Generally speaking, schedules reside at the building, equipment, space, or other aggregated levels depending upon how your system was designed. It's really important to ensure that you have an adequate number of schedules. It's equally important to ensure you don't have too many schedules, so that when an unplanned event occurs, you don't have to change several different schedules unnecessarily. Next, we'll touch on trending. An EMS is a very powerful tool with many features that can help diagnose comfort or other operational issues. One of those tools are trends, which provide a time-lapsed view of the value of a control point. In general, each control point has the capability to be trended. For example, this trend shows the electric demand of a facility in blue, along with the outside air temperature in white. Interestingly, the demand doesn't correlate with the outside air temperature. Here is another example of trend data for a hot water system with 2 boilers. The top 2 charts show the boiler status on-off, where the bottom 2 charts show the corresponding pump status. There appears to be an issue with the pump 2 status, as there's no data despite the boiler being on for most of the time. We could spend a significant time reviewing trend data, especially for this data nerd, so we'll just focus on the concept for this webinar. An EMS trend data capabilities can vary significantly, so it's important to understand the limitations of your system. Some older systems don't have the memory to store trends for more than a day or so, or they can't trend at all. In most systems, the trends need to be enabled so the system knows when to collect data. In addition, even modern systems will only collect data for a couple of weeks without an additional archiving or long-term storage trending enabled. There's 2 separate settings, one to enable the trends and one to store them for long periods of time. Despite memory being inexpensive in general these days, many EMS systems are memory constrained and cannot collect large volumes of data. Often a server is added for a system that wishes to collect and store large volumes of trend data. Reach out to your controls contractor to understand more about trending for your system. Trend data is especially important in energy efficiency projects as it can be used to define the baseline, much in the same way we discussed using meters in the last session. Trend data is essentially meter data. However, calibrations need to be considered, and the accuracy of that trend data needs to be considered. If there's a temperature sensor that's been sitting in the ductwork for 25 years collecting dust, it may not work accurately. You always want to make sure your sensors are calibrated. Lastly, we encourage you to reach out to your NHTSA's utility representative to understand how trend data can be useful for your custom savings project. Alarms are an important EMS component as they provide feedback when systems are not operating as intended. For example, the alarm highlighted here indicates a piece of equipment is turned on, which is commanded, or the output, but the status is off. So the system automatically knows there's an issue and indicates an alarm. However, as many EMS operators will attest to, and I've met many of them, alarms are often overlooked because systems generate numerous nuisance alarms, such as many of the ones we show on the screen here. We recommend that you work with your controls contractor to ensure that only necessary alarms are included. I had once visited a site way back when the alarms were continuously ignored by the operators because of the nuisance pop-ups that kept showing up on the screen. Well, one winter they had a freeze stat alarm that went off, but it was ignored. The coil froze, resulting in significant repairs and downtime. That site changed their alarm routine so that only critical alarms had higher visibility and nuisance alarms were minimized. They learned their lesson, unfortunately, the hard way. So next, we want to talk about sequences of operation. Sequences of operation are the specific instructions as to how equipment are designed to function and operate, and they're usually provided in a written form. Sequences need to consider all the modes in which a system must operate and what system components needed to operate differently in these various modes. Sequences should often define the set points and typical values. An actual value should be provided. When you're thinking about sequences, there's 4 key objectives. The first is equipment protection. The equipment must provide equipment protection and minimize damage, such as freezing coils, short cycling motors, etc. This objective is not optional and should not be traded off for the remaining objectives. Second, each building will have a different definition of reliable operation. The sequence needs to address the project's definition of reliable operation, which is also not an option. Comfort. Indoor temperatures, relative humidity, and air quality need to be maintained at reasonable levels. This is often the objective of most EMS systems. These attributes have a range of acceptable values, which, along with the owner's willingness to tolerate even a wider range, can be balanced with the last objective. The last being energy efficiency. Increasing the system efficiency can be a balancing act with comfort. Unfortunately, it's not always clear which sequence choices will improve efficiency or if they will be so complicated that it can affect reliability or even equipment protection. So why do we show energy efficiency last? Well, energy efficiency is very important, but more important is the persistence of energy efficiency. The quickest way to turn off a facility manager or controls operator from energy efficiency is to negatively impact those first three objectives. I've always believed that energy efficiency can be achieved while maintaining the first three objectives, but it needs to be planned, and the experience of the site personnel must be leveraged. Sometimes an energy efficiency sequence that looks good on paper just can't be implemented because of site limitations. Be sure to reach out to your NH-SAVES utility representative for technical assistance. Lastly, I want to highlight a really neat free online productivity tool called Control Spec Builder. It's designed to prepare bid specs for HVAC control systems based on ASHRAE Guideline 13. But it's also a great training or reference tool for people interested in understanding sequences, as it will provide you a listed sequence, points lists, and schematics that we'll actually show here in a second. So the first of which Control Spec Builder produces is a points list. A points list identifies all the input, output, and software points that we talked about earlier. It also shows which ones are on the graphics. This is typically used when designing a system or making significant changes. It's a really good way to organize your system. It also allows you to put notes off to the right-hand side, for example, to track sensor failures, calibrations, and provide new training for operators. And next, we have a sequence matrix. This isn't an output from Control Spec Builder, but is really useful for organizing your system. Here we show the sequence across the top, the words oriented vertically, and the systems that those sequences apply to as each individual row. Similarly to the points list, you can provide notes off to the right about limitations, issues with a particular unit. This is a great document for facility folks and for controls operators, especially when training new staff or working with your controls contractor. It's also great for energy engineers like myself when they're doing a retro commissioning project, so they can see exactly where a given sequence is implemented. For example, where's demand control ventilation implemented? Oh, right here. Systems 1, 3, and 5. Provides a great reference tool. All right. Matt, do we have any questions?
We've got one so far. I would prompt the audience for any more. This is one of our stopping points for questions, and then I've got one that I'll add. But the first question is that you mentioned recommending open software and use BACnet as an example. Could you expand a little bit on that and maybe also contrast it with the dichotomy of open versus a proprietary system?
Yes, great question. So BACnet is an open communication protocol. What that means is that any equipment that is BACnet rated can be interchanged without having to consider different programming and so on. So for example, if you have a controller and a supervisory controller that are BACnet that are made by manufacturer A, you can easily take those out and put in the same exact type of controller or supervisory controller made by manufacturer B. Whereas a proprietary system, say manufacturer B uses protocol alpha, that's their communication protocol. Well, that means you have to buy those controllers and that supervisory controller from that manufacturer. You can't get it from anywhere else because the language that controller uses is proprietary.
Great, thank you. And so my question is, what are the top 3 things that you would be looking for when you start to look under the hood of an EMS in terms of what some of that low-hanging fruit would be? And I'm thinking in terms of our attendees that are working with EMSs. What are the top 3 things that you'd be looking at a high level?
First one's easy. That's schedules. The number one thing you want to look at is are you turning equipment off when you can? Beyond schedules, it's really going to depend upon the systems that are in place. But generally, you're going to look for things that are usually low-hanging fruit, such as resets, temperature setbacks. Things that require programming only are really where you want to focus your attention. So instead of having to install a new piece of equipment, such as a VFD, well, it's better if you can just leverage the existing equipment you have to do resets or other sequences.
Great. Thank you. So I don't see any more questions in the chat. I would say let's continue on and talk about some of these typical energy savings opportunities.
Perfect. Thank you, Matt. So there is a whole host of energy savings opportunities, or really sequences, that we could go over. Since we don't have the time to go over each one of these, we're going to provide a handout with the slides later on for future reference. The bottom line is, to look at these sequences in more detail, please reach out to your NH Saves utility representative for support. But these sequences can range from anything like schedules and setbacks that we talked about, to optimizing building pressure control and static pressure optimization, where you're trying to vary that static pressure to reduce the fan speeds, as well as chilled water systems, where you look at chiller staging and chill water resets and so on. And the last category that we've outlined is the hot water systems, where you can look at variable speed hot water flow, for example, or differential pressure reset, similar to chill water, but on the hot water side. So again, we'll provide a detailed handout with written definitions for each of these when we also provide the slides. So next, we want to talk about retrocommissioning. We've mentioned retrocommissioning several times. Retrocommissioning is the systematic process of assessing and improving an EMS sequence of operations. It's one of the most prevalent opportunities for existing control systems. Retrocommissioning really is focused on your existing system, not to be confused with commissioning of a brand new system. I like to view retrocommissioning as a detailed audit of your EMS. Retrocommissioning should identify and repair hardware deficiencies either during the study phase or during the implementation phase by a controls contractor. Simply specifying an energy efficiency sequence is not sufficient. For example, if a demand control ventilation sequence is proposed, which includes modulating the outside air dampers based on CO2 levels, the outside air damper actuator needs to be functioning. I've seen many outside air dampers propped open with 2x4s, or the damper actuator hanging in the middle of the plenum, not connected to anything. Implementing a sequence in this case is akin to putting lipstick on a pig. Retrocommissioning should also ensure that systems are operated efficiently. Going in and only confirming or returning the EMS to its original design intent is likely to be less efficient, as newer sequences may be more efficient, and the building has likely changed since the original design. The scope of a retrocommissioning project should include reviewing set points and temperature resets, confirming outside air rates, as outside air is over too much outside air can be very inefficient. Also, this should include performing hardware functional testing, like we talked about with the outside air damper. That can be done during the study phase, or can also be done during the implementation phase. Developing a deficiencies list, again, can be often developed by the controls contractor, as those things are usually an added cost. And basically, fundamentally, retrocommissioning should identify energy efficiency control sequences. Be sure to reach out to your NH Saves utility representative for more information on retrocommissioning support. So let's return to our case study. So we talked about this case study in the past 2 sessions, 3 sessions really. This is a 20-year-old building, 3 stories, about 54,000 square feet, and it's owned by a property management company. It has original HVAC systems, where some energy efficiency improvements were made back in 2014. So in session 2, we stepped through the scoping assessment of this facility and identified several energy efficiency conservation measures, including upgrades to the energy management system. For the energy management system, we learned that there was limited control beyond basic status, schedules, and set points, and that the VAVs and reheats were not connected to the EMS. We subsequently conducted a retrocommissioning study to identify energy efficiency sequences for implementation and upgrade opportunities. So as part of the retrocommissioning study, we reviewed the existing graphics to determine which sequences were programmed and identified new efficiency sequences for implementation. For this particular project, we leveraged the controls contractor to do functional testing and confirming that all end devices are working properly as part of the implementation scope. They're ultimately responsible for ensuring that those sequences they implement function properly. However, before we can implement the new sequences, we first need to upgrade the EMS. So how is upgrading different from retrocommissioning? Retrocommissioning generally should focus on taking an existing functioning system and making it better, implementing those advanced or energy efficiency sequences, improving the design intent. Retrocommissioning generally doesn't include lots of hardware or new HVAC systems. So in this case, we needed to recall that the VAV controllers are not connected to the EMS. The communication between the supervisory controller and the VAV controller is missing, as shown here by this dotted red line. The VAV controller is not able to communicate with the supervisory controller, and so on. So we first needed to upgrade the EMS to integrate or establish that missing communication to the VAV boxes with the supervisory controller. We also upgraded the supervisory controller and graphics to provide the necessary capability for implementing the energy efficiency sequences that we identified as part of our retrocommissioning study. The controls contractor also installed a server to allow for remote connection to the system and trend data storage. So now the customer can access the control system right from their smartphone. Now that the EMS is upgraded, the energy efficiency sequences are now implemented and include schedules and setback optimization, supply air reset, static pressure reset, and demand control ventilation. For this webinar, we'll focus on reviewing the supply air reset sequence, as that was the focus of our case study throughout the past couple sessions. So returning to the rooftop unit we showed in the last session, it was very simplified previously. Now we've shown this rooftop unit with all the points that we would expect as a result of upgrading the control system with the newer graphics and supervisory controller. During the retrocommissioning study, we leveraged a similar but outdated graphic to identify those existing sequences and opportunities for improvement. Now that we have our updated graphic, we've incorporated those sequences I talked about on the last slide. Just to revisit how this system works for those who missed the last session, the rooftop units were previously controlled by the EMS. However, they couldn't see the VAV boxes because they were on local controls. So the rooftop unit basically takes return air, shown on the bottom, some of that return air gets exhausted to maintain building pressure and for economizing. That return air gets mixed with outside air to be defined as the mixed air. The mixed air then flows through the DX cooling coil, shown in the blue box here at the top, where the supply flow is maintained by the supply fan, shown to the right. Gas-fired heating coil provides preheating only, as if we recall, this system had a fixed supply air temperature set point of 55 degrees, which was maintained by the DX coil. Here we have what will be an updated graphic for the VAV boxes, showing airflow, discharge temp, heating stages, and the space conditions. Note previously we had no graphics for the VAV box because it was locally controlled and unable to communicate with the supervisory controller. So this VAV box accepts supply air from the rooftop units. Since the rooftop unit is designed to provide ventilation and cooling, the VAV box is equipped with a damper that modulates based on the space temperature. When less cooling is required, the damper will modulate down. The electric resistance heating coil is staged on to maintain the heating temperature set point. So how does this all relate to our supply air temperature reset sequence? So here is an actual sequence that actually came from Control Spec Builder. The sequence outlines exactly how the supply air will be controlled for this particular unit. So the controller will monitor the supply air temperature from that rooftop unit, and it will maintain that supply air temperature set point based on zone, heating, and cooling requirements. Well, what are zone heating and cooling requirements? This is the most important missing link. The zone heating and cooling requirements come from the space. Depending upon the control system and how that control system defines heating and cooling requirements, those can be a demand, a value assigned based on the difference between the set point and the space temperature, or it could simply be the space temperature. But essentially, it's feedback to the rooftop unit as to what the heating and cooling requirements in the space are. Well, that wasn't available before because remember, the VAV controller couldn't talk to the supervisory controller. And that's the most important piece that was missing in order for this sequence to work. So now that we have the VAV controller tied to the supervisory controller can now modulate the space supply air temperature on that rooftop unit based on feedback from the VAV box or the space. So how does it do that? Well, during cooling, the initial supply air temperature set point will be 55, which matches our existing condition that we had. And this particular sequence provides for even lower supply air temperature based on increased cooling demand. As the cooling demand decreases, the set point will be increased up to a maximum of 72. If more zones need heating than cooling, then the supply air temperature shall be reset for heating by starting out at 82. And as the heating demand increases, the set point will be increased up to a maximum of 95. As the heating demand decreases, the set point shall be reduced down to 72. Now notice the 72 is consistent between the heating and cooling sequence. 72 is important because that's essentially room neutral air. Return temperature from the space is typically going to be 70 or 72. So it's important to note that this sequence will provide room neutral air when no spaces essentially are calling for heating or cooling. That's very efficient because then it won't require any reheating, and all of the heating will be provided by the rooftop unit, which again is gas fired as compared to the electric resistance unit in each terminal box. So lastly, we want to talk about monitoring-based commissioning. Monitoring-based commissioning is an ongoing commissioning process to maintain and continually improve building performance. This essentially is retro-commissioning on steroids, or continuous retro-commissioning. Monitoring-based commissioning should continuously monitor and analyze large amounts of trend data. Typically, fault detection and diagnostics algorithms are employed, which are automated methods to confirming sequences are performing as expected. These systems often leverage separate analytics platforms, such as the example we show here on the right, to provide feedback. One of the key things to consider when you're looking at monitoring-based commissioning opportunities is to identify how these issues are going to be corrected. Simply identifying a deficiency does not result in action. I've always believed that actionable feedback is critical. Simply having this graphic on the screen that shows a bunch of issues is great, but who's going to address those issues? How is actionable feedback going to be provided? It's also really important for the persistence of savings. If the actions aren't addressed, the savings won't persist. In general, monitoring-based commissioning, its intent is to provide that persistence of savings. For example, say we implemented that supply air temperature reset. Your monitoring-based commissioning would continuously monitor the supply air temperature set point, and it would know that supply air temperature is supposed to be reset. But say all of a sudden, 6 months later, someone overrides the supply air temperature because one of the spaces is hot. So they override the supply air temperature back to 55 just to maintain that space temperature and meet a critical issue at that time. Well, oftentimes, set points get overridden and they don't get returned to their normal state. So monitoring-based commissioning software platform would recognize that, and it would provide that alarm or that notification that, hey, the supply air temperature set point is overridden, return it back to normal. Monitoring-based commissioning should also only be considered in general for systems that have been updated, are operating optimally, and have undergone retro-commissioning, because monitoring-based commissioning is intended to optimize the system ongoing and should really be a system that's already been updated and modernized. And lastly, please reach out to your NH-SAVES utility representative for more support on monitoring-based commissioning. So with that, we'll open the floor again for questions.
Thank you. So I've got one here, and the question is, how much engineering time would you dedicate to reviewing and acting on this data? He's asking for it per square foot per year, which is a bit of a loaded question, but how would you determine the appropriate amount of engineering time to dedicate to sorting through this type of information?
Well, that's a really good question. So I would actually start back with our first session on benchmarking. So it's always going to come down to how big are the loads? How much energy use does the building use? What is your EUI? If you've got a facility that has a high EUI, you might dedicate more time to looking at those systems. When it comes to reviewing particular sequences, say demand control ventilation or that supply air temperature sequence, well, first look at what the savings is per year. If the savings is $500 a year, well, you may only devote a half an hour a year to reviewing that sequence. Whereas the savings are $50,000 a year, then perhaps you would devote significantly more time. So I would always prioritize based on the savings magnitude and the opportunity that it would get override or get out of whack. Schedules are one that are always prone to being overridden. So you always want to review your set schedules first before looking at other things such as resets or economizers or DCV or other things.
Great. So you've mentioned demand control ventilation a couple times now, and I am interested in your perspective of implementing demand control ventilation in this current era that we're living in of nearing end post pandemic related to indoor air quality. How do you see implementing demand control in this current era?
Well, it's funny. I'll actually use an example that I just did for a high school. High school new construction project that we worked on. Was able to go in and identify a number of sequence for a 2-year-old building. I think there was about 10 sequences we implemented through retro commissioning study, one of which was demand control ventilation. So that site already had existing CO2 sensors that for whatever reason weren't being used. So it was a slam dunk in terms of cost. So what we did was we set up the graphics, had all the set points in there, and then we immediately overrid it to 100% outside air. The benefit there is they have the sequence. So when the pandemic ends, hopefully it ends soon, they can simply go in and release that override, and they now have the sequence that can be used. On the flip side, DCV also provides you a certain amount of feedback on the amount of fresh air in your building. Generally speaking, outside air CO2 levels are 400 to 500 ppm. And if you've got measured CO2 within your building that's 400 to 500 ppm, and you're bringing in 100% outside air, perhaps you could lower the outside air a little bit to maintain a lower set point. Typically DCV set points are 1,000 for your general office building. Maybe you lower it to 800 so that you're still providing a lot more fresh air than usual, but it also saving some energy rather than just carte blanche opening all your dampers to 100%.
Great. I have another question that I'm not sure I have a good answer for, but we'll see if you can answer this. Where can we get help writing an RFP for our HVAC preventative maintenance contract?
Ooh, that's a good one. I got to say, I don't know. Preventative maintenance contracts are definitely outside of my wheelhouse. I tend to focus more on energy efficiency, more on design. Preventative maintenance is a tough one. Off the cuff, I would perhaps just start with an MEP firm and see if they have any guidance as to where you could get help with that. Beyond that, I can't think of anything off the top of my head. I'd have to get back to you.
Good idea. Typically outside of our normal day-to-day and energy efficiency, but it's a really good question. So I have a question, and this is something, Jeremy, that you and I talked about early on when we were laying out our case study, and I recognize that we really haven't addressed it in subsequent sessions, but relative to our VAV boxes and upgrading the EMS so that we've got more visibility into those, At one point, we had talked about upgrading lighting as well and looking at network lighting controls and implementing occupancy sensors in some of the remote areas. And one of the conversations that you and I had at that point was opportunities to kind of integrate some of those occupancy-based controls with the VAV controls. And it's an interesting concept. I was wondering if you could talk about it briefly for the audience here.
Yeah, it's kind of the cutting edge of control systems where you're leveraging, say, lighting systems that don't typically get involved with controls and electrical contractors that don't typically get involved with controls to bring that data into the control system and leverage that for optimized occupancy-based controls. So I did show one graphic example of a building that we worked on where they had every light fixture in the facility had an occupancy sensor. And so they were able to use those occupancy sensors to control the terminal units in the building and do kind of standby setbacks similar to the IR heaters that I mentioned. One thing you do want to note, though, is that it does add complexity to your project. You now have multiple contractors that have to coordinate. In that particular facility, one thing I hadn't thought about was there's 400 light fixtures in the building. That's 400 occupancy sensor points that you have to integrate into a control system. And that's not simple. So there's lots of things that you have to think about during the design and implementation phase. But generally speaking, that's your holistic energy saving sequence approach is getting all those systems to talk as one cohesive building rather than a bunch of disparate systems.
Great. Thank you. That was important to get out there. So I appreciate the discussion. I have one comment on retro commissioning in general as it pertains to the NH Saves programs, and that is, you've talked a lot about HVAC systems and kind of the way to approaching retro commissioning in those types of systems. NH Saves is pretty flexible now in their approach to retro commissioning, and they also look at targeted approaches. So for a very energy intense system like compressed air or like chilled water, a chilled water plant or a boiler plant, it's another way to look at retro commissioning through NH Saves in kind of a more targeted way, some of these high energy use systems. So a number of different ways to approach it. But I want the takeaway to be that NH Saves is really interested in retro commissioning. I think that there's a lot of opportunity out here relative to energy management systems and some of these really energy intense type of end uses like compressed air. So we didn't touch much on it today, but just want to know that there's support out there for it. And I will also plug workshop number 5. I hope that you all will continue to join us next week, and we'll talk more about industry trends around buildings, kind of captured under the SMART designation here. But we're going to be talking a little bit more about where we see the industry trending in terms of electrification, and a lot of the energy management systems that we were talking about today, ways that we can integrate those with different types of pricing schemes, looking at battery storage technology, which is really emerging, different applications of that. A lot of interest in electric vehicle infrastructure, what that can mean for you as a property manager, an energy manager. And then also looking at some opportunities around on-site generation and kind of how that intersects with electrification. So should be an interesting session, a good way to kind of wrap up our series. As always, we appreciate you for being with us today. We will follow up with more information on the energy saving sequences that Jeremy touched on, went through pretty quickly today. And we hope to see you next week. So thank you, everybody, and have a great afternoon.